Okay, today I'm going to discuss the development of the next generation SMAC booster. What you see in front of you here is the original old SMAC unit, and I have here the new Gen 2 unit, which is a 5-cell 2 series stacks in parallel, just like the old SMACs, except with one extra cell per side. What this does is reduce the cell voltage from 3 volts to 2.5 volts, which also reduces heating for basically the same gas output. So you can run longer duration with less heat and better current control. So the first thing I want to do is show you, basically you guys have already seen in my other videos the performance of the original SMAC cell, but what I want to do is a side-by-side comparison of cell voltages so that you guys can see the difference and how the new design is more efficient than the old design. So the first thing, I've got the old cell set up here in the container. I've got my amp meter and my voltmeter hooked up. Alright, the first thing I want to show you guys is you can see that there's gas coming off of all of the floater plates. There's been a lot of discussion, and I've had a lot of skeptics complain that since these plates, they're not actually physically connected to the power supply. They're like, well, they're useless. They're not doing anything. They're not electrically connected. Guys, you need to understand that even though they're not physically connected to each other, they are once you put them in the electrolyte. The electrolyte is basically a liquid resistor. So when it's out of the electrolyte, these gaps they're air gaps. There's no way that electricity can conduct through the individual cell gaps. But when you immerse the step gap design into an electrolytic solution that acts as a liquid resistor, you now have V equals IR, which means that current is allowed to flow through the electrolyte, through the open cell gaps to the next cell pair. Okay, so that explains why these middle cells that don't appear to be electrically connected, why they will produce gas. They produce gas because when submerged in the electrolyte, the circuit is completed, current will flow, and gas is produced through those neutral plates. And I'm going to do this again. I've already shown this in one of my other videos, but you can see it. The gas is coming off of all the plates. It's perfectly visible right there. You can see that the gas is coming not off just the end plates, but off the neutral plates. Folks, it's V equals IR. It's as simple as that. Okay? So, my applied voltage on this old SMAC unit, I have 12.4 volts applied, okay, at the terminals. So, I'm going to show you now. This is the old design. These are the voltages per cell. You got 2.7, 2.8, 2.9, 3.1, 2.8, 2.9, 2.8, 2.9. Okay, so about 3 volts per cell. And notice, okay, if there is no current flowing through this, here's a neutral cell pair right here. Okay, V equals IR. So we have a voltage, 2.8 volts. Okay, we have an R, the resistance of the electrolyte between the small gap. So therefore, we must have a current because V equals IR. So you can't tell me, skeptics, and don't tell me, because I'm showing you right here that these neutral plates do conduct electricity and they do produce gas. I mean, you can't get, here's the proof. I mean, read the meter. There it is. So you can argue all you want, but you're going to be wrong because the proof is right here in front of you. Okay? So that puts the floater issue to rest. The SMAC has put I'm laying the law down on that. You can argue all you want, but you're just wasting your breath and you're wasting your typing skills because I already know it works. So, there's just no more to be discussed about that. So, you see about 3 volts per cell on the old design. Applied voltage is 2.4 volts. Okay, so now what I'm going to do is I'm going to switch over. That's the old design. I'm going to take this puppy out of here. and I'm going to put my new 5 series double parallel design in the electrolytic bath. We're going to hook up the same applied voltage. Okay. So we're going to go and, yeah, look at that, gas on all the cells. Imagine that. So our applied voltage dropped a little bit because this is a different configuration, but we still run about 12.2 volts. Okay, applied voltages. We're running 9.5 amps. So let's do a volt per cell on this guy. Look at that, 2.4, 2.3, 2.3, 2.3, 2.4. I'm going to the nearest tenth, obviously. 2.3, 2.3, 2.3, 2.3, 2.4. Now, the first thing I want to comment on is look at the consistency of the voltage. You can tell there's very little parasitic current loss because the voltage across each cell pair is fairly consistent. I mean, there's very little voltage loss due to parasitic current losses going around the edges of the plates. And one of the reasons for that is if you can't really see the difference between the two because of the curved edges on the outlet plates. This is a flat plate design. I've actually decreased this small gap, this small open cell gap, by 0.6 millimeters. So these are 1 millimeter gaps versus 1.6 millimeter gaps. Okay, so you require less of an electrolytic concentration for the same amount of current because there's less resistance now between the plates. Also, the plates are taller. There's more surface area, which reduces the current density, which helps not only to produce more gas, but to reduce heating effects. And this helps contribute for a more even voltage spread across the cell stack. So instead of running about 3 volts, now also remember in your car it's about 13.8 volts. So you're actually over 3 volts on the old design. On the new design, you're still under 3 volts. So there's less heating with the new design, and it still fits inside the 4-inch container. I can show you that right now. Because of the flat plate design with the no curves, I can get the same unit to fit inside, or the new unit to fit inside the old container, which is awesome. Which means I haven't sacrificed, because one of the main constraints is space problems. You guys don't have enough room to put these things in, so we still have the 5-inch outside diameter, 4-inch inside diameter container, but we now have 2 extra plates on the outsides.